So hi everybody and welcome back to C++ tutorial series for absolute beginners. This is video 144, and in this video we continue with our examples with the move constructor. And like all time I use CPP reference com site. Here you click on language, then you can go here to the classes, here to the move constructor. And we talked already about these examples. We finished here the first part. Now we will jump here, and again I use here the compiler explorer. You can use here an IDE. So, and like I said, we have already discovered this part here. Now we jump here to these lines, and here we see, first of all, this is just an output stdc out. We want to put something out, and here we see that we want print a1s, which is just our variable s from the object which we created. But interesting is, what is this std quote doing? Actually it is just adding this quotes here around whatever this is, and you can see this here in the output. Here it says before move, this is this part here, a1s, this one, and then you can see test is actually our value. This is a1s, and this std quote is just adding this quotes there, and this will be needed later. You will see this in a moment, but we go on. We can see here again we are just outputting now the value k, which is -1, and you can see these two values which we have here are the default values from our struct. You can see the constructor here has default values, so we have not passed in anything. They was just here, and the constructor is just assigning these values to them, and we just printed out these values to see what happens later. Okay, and we jump now to the next line, which is this one, and analyze it. Let's see what we have here. First of all, A2, we are trying to create a new object with the type A, which is our struct again. So in other words, we are trying to create an object with all the settings here. Okay. And the next thing, what we are trying to do here is we are just taking A1, which we already created with the default values test and -1, and then we are using it with std move. Question, what is std move, or what does it do here? Answer, we have a1 which is an L value, and we try now to change it to an R value so that we can use move semantics. And another question, why we are doing this? Why not just take a1 and then just use here assign to a2? Answer, we are doing this because we want all time try to use move semantics if possible, and the reason for that is performance. We learned that move semantics are much faster because it's more or less like a pointer switch, and this boosts a lot of the performance if a1 is a big data, so we don't need a copy of it. Also, you will see that std move is more or less like a static cast. It is similar, which is doing just taking the type what we have here. In this case we have, for example, just this type here, and it is adding two ampersigns to it, like so, that we can use the move semantics, because we learned when we jump here again to A, this one can only bind to R values, and yeah, it must be an R value, and most time when you see this double ampersand, it is an R value when you use std move, because this one is changing the value category. But careful, we learned also, even this one looks like an R value when it's bound to a named variable. It is not an R value. So don't get irritated by this again. I just mentioned it, but when you see std move, all time it is trying to convert just L value categories to an R value category. And that means we can use move semantics. Okay, now we have analyzed that this one is just changing the R1 to an R value so that we can use it for move semantics. And let's see how we go from here to here, because we want to try to create a2. So what happens now? Let's jump to the struct A, because we have to check, and we see the compiler can choose here two things. What can the compiler choose now with our converted a1 here to an R value? And we have the option move constructor can bind to an R value because we have here the special case const can bind to an R value. Normally it could not bind to an R value if we have just a ampersand, but with this one we learned yes, it can bind. But we have here another constructor which can only bind to an R value, which is our move constructor. So the compiler has here again to decide, and the compiler will all time decide move constructor if possible, because higher priority, because of performance. And in this case the compiler is just choosing this one. So in our case, when we go and try to create A2, it is using the move constructor, and we can see this here on the output move constructor A called. But interesting is here the assignment. What I mean with that is here we have A1 created, and here we create A2, a new object, but we are using A1, the object which we already created, and we are using move semantics with it. So it is interesting to see what happens with A1 after we use move semantics, because in our first example here we have also created an object that was this temporarily unnamed object, but the problem here was it was a temporarily unnamed object which is more or less deleted, or it's gone after this instruction here, after this semicolon. Here with A1 this is not the case. After this semicolon we have still A1 here, and now we are using a move semantics with A1, and we learned to move semantics is taking away the resources or the settings from A1, and we will see now how this looks like. Okay, and now let's see how the move constructor is taking away the resources of A1 and in which state A1 is afterwards. For that we scroll up, we go to the move constructor here, and here it is defined how the resources are taken. Okay, the first step is when I scroll down again, I take first A1 because A1 is the object which I have converted to an R value with std_move, and I pass it where? I pass it here to the constructor parameter list as an argument, and it will bind here to this named object O as an R value, because this parameter accepts only R values. Okay, so our A1 is bound to this named variable O now, and what we learned is when it's bound to a named variable, now it is an L value. Next step is we are trying just to assign the variables from one object to another object. And how we do this, let's check this line here. First of all, we have our O here. This is our A1 object, and you can see we are using O.s. So think about, we are using here A1.s, and A1.s is now using here again this move semantics, and I already talked about this. The reason why they are using here again the move semantic is because std string is not a primitive type, which means it can have also all the constructor, move constructor, assignment operator, and all the things what a programmer can create. And that's why they are using this here as well to avoid performance loss with strings. And I made this example. You have to be careful with strings, because in this example we have just one word, test, as a string. But think about it, there is a person who have a dictionary with 10,000 or million words, and now they don't want to copy million words, they want also use move semantics. That's why they are using here as well this std_move. Okay, but what happens here with the value of object A1? Because we see O is bound to A1, so it says here more like A1.s is here, and we are trying to assign now with this std_move A1.s this to s, which means just we're taking A1.s, which is test. We learned this here. A.1s is test, so we take test here and just assigning test here to the object A2. That's easy, okay. But the real question is, what happens now with A1? Because we take the resource. And the answer is, the compiler must let A1 here in a valid state. What does this mean? The answer to this question is, it means that when you finished here this expression after the semicolon, that A1 is afterwards still usable. What does this mean? That this means, for example, we have here the next line, I can still call and use a.s, for example. So I don't get here an error because I just took the resources out of it. That means here in our move semantic, this assignment must let A1 in a valid state. And how does the compiler let this one now in a valid state? Let's use for this question a very simplified answer again. The compiler will try to use almost no additional resources to create a minimal valid state, which means without allocating memory, without doing anything additional. It is just minimal to create it and to let the object A1 live in a valid state. It's very simplified, but otherwise we have to dive into this again. We skip this part. Think about it like so, and you can see this here, for example, in our example later. It is just empty. It is empty but usable. That empty means still usable by the programmer. All right, let's go to the next example to see this a little bit more in detail. Again, what we try to do again, okay, O is our A1.k. We try to get the resource of it with the move in the assignment here. And this std exchange is a special function here, which is actively assigning to the old object, in our case, our old object is A1, a special value. So this one is not internally managed by the compiler. It is managed here by the programmer. That's a big difference compared, for example, to this one, which is perhaps made by the compiler. So this means it is easier for us to understand how this move semantic works. So here we can see the old value O.k, which is A1.k, is taken. It is assigned to k. So our object A2 becomes -1 because we take this old object. And now interesting is this std exchange shows what happens with the old object. Old object is our A1. A1k becomes 0. So in this case, it is actively set to 0. For example, here in our std move example, we don't see to what it is set by the compiler. Here we see it. So, and when we jump back to our example, because we have finished now this line, we have called here the move constructor, we have used all the move semantics, and now we are here line 58 and 59, and we can see the output. Important is we check not A2, we are checking what happens to A1, because we want to see if we can use this later. And if we can't use it, we would normally already get here an error, but we get not an error, which means we can use it. And now we want to see the values of A1, and let's check it. So it says here after move A1.s is empty. You see here nothing, that's why they used here the quotes. Here we can see they used here the special function quote, because normally this one is empty, so they made it just a little bit visible to understand for us. That's why they used here this function quotes. We can see it. Normally it's empty. And again, this empty was created, let's say, by the compiler. All right. Let's say the compiler has managed this one here because we don't see how that was made. And the other example here is our a1.k. And we see this one is set to 0. And we just saw this was managed by the programmer because the programmer used here the special function exchange and set the old value to the old object to 0 actively, which means this one is set to 0 and we can see that. The last question, what does this mean? The answer is this means we have used move semantics, yes, to create a new object and take the resources of A1, and this gives us a performance boost if the object A1 would be very, very big. And this means also we destroyed not A1, we just let it in a valid state, which means if we want to use A1 later down here, then we have to assign new values to S and K because they are not the same anymore, because they are taken away. But important is we still can assign new values to it and use A1 like normal. And we can see this here with A1 with the output of A1K and this A1S here, because you can see it is just not the same object like before. Here we had the real useful values provided by the programmer. For example, here we have normally compiler created values, which are normally not useful because here you have to reassign them to make use of them. So these are the basics about move semantics. If you understand that, that is perfect, because now you know the basics and can build up on this. And we will see the other examples here. They are similar, but they build up on this core principle. And with that said, if you have any questions like all time, write in the comment section. See you in the next video. Have fun. Bye.